So I'll be talking on reliability analysis of safety critical systems. Before discussing this topic, let me make you understand what does actually this topic means and what is the essentiality of this topic. What is the motivation of this topic? So if you see nowadays, like the safety critical systems are being used in various applications. And safety critical systems are those systems, the failure of which can lead to catastrophic disasters, even it can lead to the loss of human life. And if you see the domains, the various domains that include aerospace, automobiles, nuclear energy, defense, medical domain. So these are the very critical applications and where we really make the use of safety critical systems. And if any of these safety critical systems fail, then it can lead to like very severe consequences, and in fact it can lead to loss of very critical facility or loss of human life also. And that is the reason like the reliability requirements are very high for such kind of systems. And so specifically like if I'm talking with the reliability analysis, means there should be some method from which we can quantify the reliability, and so that we can get a good level of confidence before deploying these systems into the real operational life, that it will really meeting all by intended specifications. So now if you talk about reliability, what does reliability mean? So reliability, it is a probability of failure free operation of any system and up to given period of time and under certain environmental conditions. Now this definition is very important, and each and every word and terminology is very important to understand. As I said, it is the probability. So probability, we know like it ranges from 0 to 1. So if we talk with respect to the quantification of the reliability, its value ranges from 0 to 1. And it's the probability of failure free operation of any system. It means success of the system, probability of the success of the system. And next, up to given period of time. Now here time is very important. If I say it is reliable, I have to definitely tell up to what period of time I'm talking about, because I know nothing is reliable for infinite period of time. Even if you consider the human being, they are also, I mean, probably if you can look back to your childhood time, you may be having some of the friends, and you may be thinking like these are the friends which are the best friend and will remain throughout the life. But as and on time passes on and dynamic situations gets changes, the pride and interest gets changes, the priorities get changes, and depending on the current scenario, you may be finding like most of them have now may not be as good friend as you have started making new friends. So that is why we have to really talk up to what period of time I'm talking about if I'm talking with respect to the reliability. And that is the reason the warranty of the different, and definitely if human is not reliable, so all the created applications of human being definitely will not be 100% reliable. And that is why we have to talk up to what period of time we have to we have to specify up to what period of time we are talking about. Now so there it means it is now very much essential because of the criticality in nature of safety critical systems. It is very much essential to perform the reliability analysis. And the second thing in the definition I said, it depend like under is under up to period of time under specified conditions. Now it is very important because any product can be reliable, can be more reliable in one situation than in other situation. For example, suppose you go and purchase a refrigerator, and the vendor gives a warranty period of 1 year. Now when you come back with this refrigerator at home and you just throw this refrigerator from example say 14-story building, it will collapse. And now you cannot go back to the vendor and say, look, you have given the warranty period of 1 year. Now I want the replacement of this product back. The vendor will say, look, you have not followed the specified or the operating conditions. Because any product has to be work on specified operating condition. Then only the warranty will be void. So what I wanted to conclude over here with the definition, the 2 points are very critical. One is reliability depends on the time, so it is a function of time. The second one is it depends on the operating conditions or on the environmental conditions. So these two are very important. So we'll be just discussing how we can quantify the reliability of the safety critical systems. So let us have a look on today's agenda. So I'll be talking about reliability only. I have already discussed. Now we can see what are the traditional methods that are being used for quantification of the reliability, and then we will see like a battery net and modeling of the system. Now battery net, it is a kind of tool, and it is a modeling tool, and it is basically a graphical as well as mathematical tool. While graphical because we can represent any system in the pictorial form, uh, depicting what would be the behavior of that system using this battery net modeling technique. And why it is a mathematical tool? Because we can embed the mathematical knowledge to derive many mathematical attributes which can bring out some of the critical insights of that system. So particularly we will be seeing how it can be useful with respect to the reliability quantification. And so we'll be discussing what actually the battery net is, and what is the history, origination history of this battery net, and what are the benefits that can be drawn from this battery nets. Then we will see what are the important property of the battery nets, what are the analysis techniques, and thereafter I will propose I will discuss the proposed reliability framework, in which I will be discussing what all the important phases that has to be executed to quantify the reliability of any uh, safety critical system. And we'll be taking a real case study, and we'll be trying to demonstrate or illustrate our approach on this real case study so that the participants can have a real feel like how it can be used in the real practice, and then we can conclude the session. So this all I have talked about. So anyway, like if you see like mathematically the definition of reliability, so let us assume x is a random variable which represents the time to failure of a component. Then because time to failure means it should at least work for this period of time. It should not fail within this period of time. So the reliability of the component at time t, because as I said, reliability is a function of time, is given by, that is the probability that x must always be greater. This will represent the reliability, because as I said, X is the random variable, which is basically representing the time to failure. So before this, it should not fail. So X must be greater than T. If I'm talking like the reliability as a function of time T. Then from the mathematical knowledge, we can write it is equal to 1 minus P is X is less than is equal to T. While X is less than is equal to T, it represents the probability of failure before time specified time T. It means it is a failure probability. So we can equate it to 1 minus failure probability, which is also a function of time. Now failure probability is nothing but we can name it as unreliability also. So if you can see from the total probability law, the reliability, the sum of reliability and unreliability will always be equal to 1 because both are representing the probabilities. Now let us have a look on the traditional methods which are being used for reliability prediction of safety critical system. One method is known as the reliability block diagram. And in reliability block diagram, the concept is we think because we know like any system is composed of several components, and those components can be arranged in series and parallel combination. So this logical structure basically of the system constituting all the layout of the components is known as the reliability block diagram. And the layout of the component definitely affects the system reliability, overall reliability of the system. For example, suppose if two components C1 and C2 are arranged in a series, and suppose like one system contains only these two components, then the reliability of the overall system can be computed by the series formula of reliability, that is R1 into R2. If R1 and R2 are the reliabilities of components C1 and C2 respectively. And similarly, if they are arranged in the parallel combination, we can use the reliability of, we can use the formula of parallel component reliabilities. So in this way, we will be able to find out the total reliability, the entire reliability of the system. So it means we'll have to particularly, we should know the reliabilities of the subcomponents of that system. And the reliability of the overall system will definitely be the function of the reliabilities of the of its constituent components. Now there is a second traditional method that is being used is known as the reliability graph. So reliability graph is also very much similar to reliability block diagram. Only the notation or the basic building blocks are different, and it consists of set of nodes and edges. It basically contains directed edges, and the nodes represent the link between two components. It represents the connectors between two components, and the arc basically represent the components in the system. So if you can see in this figure, the left hand side, the left figure is representing the reliability graph, where A, B, C, D are the vertex, and which represent the connectors, and V1 up to V5 are the big components. So this reliability graph can be transformed in equivalent reliability block diagram also. If you see the right figure is showing the reliability block diagram, where V1, V2 and up to V5, these are represented by the components, and these ABCD we are representing it by connectors or the connections between these components. And again, this figure can be solved by assigning the basic components reliability and using the series and parallel formula of the reliability. So we can come to know the reliability of the overall system. Now the next very prominent method of reliability is known as the fault tree method, and it is basically a deductive technique. Deductive in the sense we start with the observation and try to deduce the cause of that observation. For example, if I say my laptop is not working, then the cause could be probably the power button is fail, the power supply is failing, the hardware is failing. Now we have to deduce further. For example, if I say my power supply is failing, so power supply could be from either there could be loose connections, there could be the reason could be wire breaking, wire has break, there could be the reason that power is not coming at all, there could be the loose connection, no loose connection from the socket socket side. So we are trying to deduce further and further basically. Or if I say hardware is failure, so either hard disk is not working or some ICs is not working. So we can keep on deducing and we try to find out the basic cause, and we can assign the probability of that basic cause to solve the top level probability. That is the observation probability, and observation was laptop is not working. So for example, if I say uh, the power failure and there are the two only basic causes, that there is a loose connection and there is a wire break. So both condition must satisfy, then only the power will fail. No, sorry, any of the condition if satisfied is satisfied, then only the power will fail. So then we if the basic causes are arranged in OR logic, then definitely from the probability law, the probability of the power failure will be summation of those individual probabilities. And if they are arranged in the AND logic, means both the condition must satisfy, then definitely from the probability law, both probabilities must be multiplied. In this way, we can keep on deducing, and we can find out the top level event. So basically here we are making the use of AND gates and OR gates, and then we can find out what is the probability of failure of my laptop. And for computation of the reliability, we can subtract it by 1, as we have already seen that the sum of reliability and unreliability will be equal to 1, right? So in this way, we can find out the reliability of the overall system. Now, these models that we have seen so far are the traditional models, and are not able to capture the dynamics of the system. Because one thing I had said very clearly, that reliability will also depend on the scenarios, basically the current scenarios or the dynamics of the system. So definitely if there should be some modeling technique where we can embed these dynamics, or which will be able to capture these dynamics, then definitely we will be able to give more accurate estimates of the reliability. So for that, the people started devising different type of methods for reliability prediction, and those methods are known as state space methods or state space models. And where the concept was Uh, let us decompose the system into various states that can be confronted throughout its operational time. For example, if you consider the human can having the state running, eating, sleeping, talking, walking. These are the various states. And states can be broadly categorized into behavioral states and failure states. For example, if I say human has confronted an accident, so it is a failure state. So to find out or to compute the overall reliability of the system, there could be two methods. If I'll be able to find out the probabilities of being a probability of the system being in every state, and add all the probabilities of success states, then it will give the reliability figure. Or the other ways out is, if I'll be able to find out the probability of system being in failure state and summing all those failure states and subtract it minus 1 by 1, then again we will get the reliability of the overall system. So I mean to say, generally the failure states are very less, so it is better for easy computation. Well, like if we can sum up all the failure probabilities and we can subtract it by 1. Coming back to the state space model, there are the various models that are existing for a state space model. One of the prominent model is known as Markov model, which has been given by Andrew Markov, and he was a Russian mathematician, and he introduced this concept almost in 1940s. And he said, like, if you talk about the basic building block of this model, it consists of set of states and the set of transition probabilities among those states. Means from one state to another state, what is the transition probability? For example, if I am sleeping, now from sleeping state I can go to uh, walking state, or I can go to sitting state. I mean, what is the probability of being in particular state? So it can easily depict the stochasticity of the process. So stochasticity, anyway, this is a very important term. The process can be categorized into two main categories. One is the stochastic process, and second one is the non-stochastic process. Non-stochastic process are known as deterministic process also. Now, what are the deterministic process? The process whose outcome is 100% guaranteed. Those processes are known as deterministic processes. For example, if I'm having a pen and I drop down that pen, I can 100% guarantee like it is going to drop down because of the gravitational force that is acting on the earth. While non-deterministic processes are those processes uh, which are whose outcomes are not 100% guaranteed. So all the even human is not human is also stochastic in nature. So all the processes created by the human being are stochastic in nature. So these Markov models are having a capability to depict this stochasticity of this process. So for mathematically, if you see, like if there is a system which contains only two states I and j, and let qij be the transition rate from state I to j, then we can define the transition rate. Transition rate is means the number of times the per unit time it is transiting from one state to another. So the transition, so definitely all, if you sum up all the transition rate from one state to all other states will always be 0. So the QII will be definitely minus summation of Qij, where j can be from I to n, but it should not be I. And then we can define a transition rate matrix in which we can write all the states in rows and column, and we can fill in that matrix elements by computing the transition rate from one state to another. And this matrix is also known as generator matrix also, or transition matrix also. Now coming to next concept, next modeling technique is Patrinet. And this concept basically has been introduced by C.A. Petri, who was a German PhD scholar in 1960s. And he has introduced this concept to solve the various challenging problems, industrial problems, and to model the stochasticity behavior of the processes. And as I said, it is a very good graphical tool as well as a mathematical tool. And there are a lot of benefits that can be drawn from the graphical representation. For example, suppose I'm a very big businessman and I have a business of ventilator development of the ventilator. And but I outsource the development. I only uh, study the market and analyze the market, and accordingly I give the specifications to the development agency. So what is the benefit that can be drawn from this Patrinet model? The development agency can model all the requirements in a very pictorial format, and it can be illustrated to me, and where in the requirement phase itself I can point out what all the requirements that has been missed and what are the ambiguous requirements, and a lot of discussions can be taken up during that period of time. So this will give a very clear understanding to the development agency that actually what kind of product that we are looking for, because most of the things are basically not understandable in the written format in terms of requirement specification. And if you see in the industries, generally the project basically uh, is divided in the effort that we put in the development of the project is divided into 40-20-40 ratio, where 40% of the effort has to be given in requirements and design analysis, and 20% of the effort has to be given in the implementation analysis, and now the 40% effort has to be given in the testing phase. So and if in the testing phase, suppose I come to know we are not meeting the requirement, and then we may have to again start with the requirement phase itself. We have to again go back to the very first phase of the system development life cycle, which can basically turn into slippage of schedule, and will have to, as a businessman, I may have to lose a lot of money from which I had already postulated that if within this stipulated time, if I'll be able to deploy my product into the market, I'll be able to earn so much of profit. So in this way, it is a very good tool, and we have, as I said, it is a very good mathematical tool also, because we can use the mathematical knowledge to bring out a lot of insights of this particular system, and it will give a very good confidence on the robustness of my, or the integrity of my product basically. So it is the best communication between theoreticians and practitioners. And if you look back into the history of this Patrinets, covering all the important milestones, As I said, in 1962, the C.A. Petrie is introduced this concept in his PhD dissertation, which later on has been uh, recognized as having potential to model most of the critical aspects of the system. And with this objective, MIT USA conducted a conference on concurrent system and parallel computation in 1970s to discuss whether this modeling technique can be used for concurrent systems or for the parallel computation. And the outcome was very beneficial. The conclusions were very beneficial, and the then they thought of enhancing the modeling technique also. And with this objective, they had decided to conduct the next conference in 1975 on Petri nets and related methods. And then its industries also started its uses. And looking into the industrial demand, the Germany started a course on general net theory of processes and system in 1979. And then people started discussing what kind of applications that can be modeled. And with this objective, the France conducted a first European workshop on applications and theory of Petri nets. And then in 1985, uh, people thought of increasing more and more, modeling power of this Petri net. Because, for example, if I'm interested to model a real-time system where the timing information is very important, so definitely the model must contain the timing information. And so in this way, like the various flavors of the Petri net started coming up. And one kind of Petri net that was containing the timing information known as timed Petri net. So the first Euro International workshop on timed Petri net was conducted by Italy in 1985. So these are the very important milestones where it has boosted up, and the people started appreciating and working on increasing more and more modeling power to solve more and more industrial challenging problems. Now, if you see the Patrinet applications, basically it is having a potential to model almost all kind of applications, whether it is concurrent systems and control systems, safety critical systems, fault tolerance systems, hardware systems, software systems, any kind of systems. Now let us see the building blocks of the Patrinet, the working mechanism of the Patrinet. So just to appreciate, I have taken a very small example. Suppose I want to model a very basic chemical reaction, that is hydrogen plus oxygen that gives water. I want to model this chemical reaction. So this figure, if which you would be seeing, it is a Patrinet figure. And first we will discuss what are the basic building blocks of this Patrinet. So if you see, there are the three big circles, and these three big circles are known as places. So there are the three places in this figure, and I have used one place to represent hydrogen, second place to represent oxygen, third place to represent water. And the next building block, if there is a rectangular bar, which is known as transition. So here there is only one transition represented by T, and then there is a directed arc which can basically connect any place to transition or transition to place. So it means there cannot be direct connection between place to place or transition to transition. So if you see in this figure, there are the three directed arcs, and which are connecting hydrogen place to transition T, oxygen place to transition T, and transition T to water place respectively. And we will see like what is the importance of these building blocks while we will be discussing the working mechanism. Now the next is we can see like the numeric number that is assigned on the arc, and that numeric number is known as weight of the arc. And if we don't assign any weight of the arc, by default the weight is 1. So in this figure we can see the 3 arc has weight 2, 1 and 2, because in 1 I have not assigned any weight. Now the next building block is you can see there are the embedded circles inside the place, and these embedded circles are known as tokens. So you can see the hydrogen place contains 2 tokens, oxygen place contains 2 tokens, and water place contains no token. So now this distribution of the tokens in the in all the places basically represent is known as marking, and it represents the state of the system. So it means if I want to change the state of the system, the distribution has to be changed. So this is the initial distribution. These if you see in the hydrogen contains 2 atoms. So these 2 atoms I am representing by 2 tokens. And oxygen also contains 2 atoms, so which I am representing by these 2 tokens. And now, so this basically this is the initial state of the system, the figure that you are looking, and this is representing the left hand side of this chemical equation, what hydrogen plus water, and now it has to be converted. Sorry, hydrogen plus oxygen, and now it has to be converted into water. So the distribution of the tokens will be changed, and how the distribution of the token will be changed. Now there are some specified rules. Now I am discussing with the working mechanism. So to change the state, any of the transition must be fireable, and the transition can only be fireable if it is in enabled condition. Now there is a criteria of the enabled condition, that a transition is in enabled condition if all the input places contain sufficient number of tokens. Now let us see. There is a concept of input arc and output arc. So the arc which are terminating to that on an entity, for that entity those arcs are input arc, and from the entity where the arc is emerging, for that entity that arc is output arc. So in this figure, hydrogen place contains 1 output arc, oxygen place contain 1 output arc, transition T contains 2 input arc that are coming from hydrogen place and oxygen place, and 1 output arc that are going to water place. Now coming back to enabling of the transition, as I said, the criteria is input place must contain sufficient number of tokens. So the places which are connected from the input arc are known as input place, and which are connected from the output arc are known as output place. So for this transition, the hydrogen and oxygen places are known as input place. So if this is fireable, or for the enablement of this transition T, oxygen place and hydrogen place must contain sufficient number of tokens. and sufficiency of the tokens will be decided by the weight of the arc which are connecting by these places. So if you see the weight of the arc which is connecting this hydrogen place and transition T is 2. So it means hydrogen place must contain at least 2 number of tokens. Similarly, oxygen place, the weight of the arc which is connecting oxygen place and transition T is 1. So it means oxygen place must contain at least 1 number of tokens. So here we can see this criteria applies and or this criteria exists. So there will be movement of tokens, and the movement of tokens occurs from the input places to output places. Now, how many movement of the tokens from the input places and to how many number of tokens will be deposited in the output place? That will be again totally governed by the weight of the arc associated by this input place and output place. So here the weight is weight of the arc which is connecting the hydrogen place and T is 2. It means that 2 tokens will be moved out after firing off transition T, and 1 token will be moved out from oxygen place because the weight of the arc of which is connecting the oxygen place and transition T is 1 will be moved out. So on total 3 tokens will be moved out from input place, and how many tokens will be deposited in output place? So that will not be depending on the weight of the that will not be depending on the how many tokens have been moved out. That will again depend on the weight of the output arc. So weight of the output arc is 2. So only 2 tokens will be deposited in the water place. So it means there is no concept of conservation of tokens. The movement of the tokens will be totally governed by the weight of the input and output arcs. So this is the initial state of the system, and after T fires, the 2 tokens has been moved out from hydrogen place and 1 token has been moved out from oxygen place and 2 token has been deposited in water place. So this is the next state of the, so here the water has been made. Now you can see here in this case this transition tree is not fireable because it is not an enabled state and it doesn't follow the enabling criteria, because as I said, all the input places must contain sufficient number of tokens. Although in this figure oxygen is containing sufficient number of tokens, which is 1, but hydrogen is not, which it should contain 2 number of tokens. So that is why now the process will remain in this state only, and this is the end state. So it will only contain 2 states. So this is the now the distribution of the state has been changed. So there is a concept which I want to introduce, concept of reachability graph. Reachability graph basically represents how many number of states can be possible in a system throughout its operational time. So we can see, for example, in this chemical reaction, there can be only two states. One state is this, and second state is this. And as I said, the state is represented by the distribution of the tokens, and distribution of the token is 2 to 0. So 2 to 0 is one state, and after firing T, it converted into 0, 1, 2. So this is the reachability graph. So that was the basic working mechanism of this Pattern Act. Now there is one important property in the Markov chain. As I said, I have just showing the representation of this Markov chain. As I said, it contains basically 2 state. For example, there is a system which contains only 2 state, S1 and S2. So it can be represented by this, and it can transit from S1 to S2 and vice versa. And and always the current state will depend on the previous state and not on more previous states. So if suppose there is a sequence of random variables x1, x2 up to xn with the Markov property, then what does Markov property says? That the probability of my system of being in n1 n plus 1 state, if it is x, it will only depend on just a previous state, not in the more previous states. So it can be written as, right, x and is equal to x. Just I have taken a random example of the reachability graph. This left is a reachability graph. It is showing the distribution of the tokens in the place. For example, there is a Patrinet figure in which there are the 7 uh, places and the distribution of a token like this. And after firing of transition T1, the distribution changes like this. And similarly, we have drawn the complete reachability graph, and it can be equivalently transformed into the Markov chain, because this is representing state. So we can write it in the notation of Markov chain. And this is lambdas. All the lambdas are transition rates, which can be used to derive the transition probabilities. We can see how we can derive. Transition rate is number of transitions per unit time. It's known as transition rate. Now, let us discuss our reliability prediction framework. So we have already discussed the background knowledge or the base knowledge that are required to execute in our framework. And so our framework basically contains 3 stages. One is the Patrinet model creation. We have to create the Patrinet, and that we have already seen while discussing a very small example of chemical reaction. In fact, we will see when we will be taking a real case study and try to see how we can illustrate this framework activities. Then the Patrinet model can be converted into the Markov chain. That also we have seen how we can convert into the Markov chain by drawing the reachability graph, and that reachability graph can be easily converted into the Markov chain. And then in the third phase, we can compute the reliability. We can solve the Markov chain and we can compute the reliability. Now, before actually starting with the framework or the case study, let us understand some of the important concepts that we are going to use in. So let us assume pi it be a probability that a component is in state I at time t, where I could be failure states or behavioral states. And as I said, this I can have because the states can be behavioral states also and failure states also. So as now this is second one is, as t goes to infinity, these probabilities converge to the stationary distribution. Now this is a very important statement. For example, consider a glass, and that glass is filling with the water, and suppose like the water is in a zigzag, water is zigzagging, and so this is the initial state, and after some amount of time the water will completely settle. And consider the similar case. In place of glass, you just take the very big container. For example, the container at the size of room. So what you can do, you can fill that container with the water, and you will find there will be the water waves which will be zigzagging, and it will really take a lot of time, a very longer period of time to settle down completely if you compare the time taken by the glass, the water in the glass to settle down. So what I wanted to make it out over here is if your system is complex, definitely theoretically, I have assumed if time tends to infinity, all these probabilities converge to the stationary distribution, and which can be computed by these two equations, which are very important, and the concept is very simple. First, the sum of probabilities of all sum of the probabilities of a system in being any of the states will always be 1. This is by total probability law. The second equation is very important, and let us assume, let us consider the same case of when we were filling the water in a big tank and we were putting it down. And suppose at the initial point of time, the water was very zigzagging, and the state of that zigzag is S1. Now suppose after delta T, it is turning to the second state and it is trying to propagate towards the settling state. Suppose that is next state is S2, which have lesser intense waves, and this S2 will depend on S1. S1 is the initial state, and the transition probability from S1 to S2. So S2 can be written is equal to S1 into transition probability from S1 into S2. And similarly, after further delta T, it turns into the state S3. That will again depend on S2 and the transition probability from S2 to S3. So S3 can be written S3 is equal to S2 into transition probability from S2 to S3. In the similar fashion, if you see, suppose the water has completely settled down at a state Sn, and now definitely then Sn plus 1 state will remain same because it has already been completely settled down. So Sn1 will always be equal to Sn, but the equation, if you use the same equation, Sn1 is equal to Sn into transition probability from Sn to Sn plus 1, it will be equal to Sn1 is equal to Sn. So Sn is equal to Sn into transition probability. So this is the same equation. The second equation is, it is the stationary probability is equal to the stationary probabilities of all the states into the transition probability matrix, we have said, because we are not talking only about one state. Suppose your system has n number of states, so we have to talk about the matrix in the form of matrix we have written. And now let us take a case study of a communication module of it. Suppose there is a safety critical system, and the safety critical system, suppose it is composed of the sensors which is reading some of the data from the field, and it is passing towards the embedded unit, which is basically processing some of these values, and those values are displayed in the graphical unit, and it can also send to the actuator to basically actuate some of the mechanical devices or field devices. So suppose there is a communication module, and which is very critical, because if I'm communicating the wrong data, definitely the decision will be wrong, which may lead to the failure of the safety critical systems. So this so to understand, let us first understand the algorithm which is involved in the communication module. So the algorithm is very similar, like if I want to talk to my friend, what I will do, first I will dial the number to my friend, and then I will say hello, and then he will say I will wait for the acknowledgement, and suppose if I don't get the acknowledgement, I will again say hello and wait for the acknowledgement. And after couple of times, after trying a couple of times, if I am not able to get any response, then what I can assume, I think the connection is lost and I can cut the call and I can retry. So the same concept has been applied over here. Suppose there is an embedded unit which is capturing the data from the sensors and it is sending to some display unit. So when embedded unit sends a new packet, because the data are sent in the form of packets, the value of the count is set to 1. And embedded unit waits for the acknowledgement, for example, for T1 amount of time after sending packet. Now suppose if embedded unit receives acknowledgement before T1 time, then we can declare that the packet send is successful. And for that, I have kept one semaphore variable, which is a binary variable that I can change it to the complement. And as I said, I will try a couple of times. So let us say that couple of time is n, and I'm after every packet send, I'm increasing the value of count, which I have maintained one variable. So if count is less than n, and if I'm not able to get any acknowledgement, then the embedded unit keeps on transmitting the packet, and it will increase this count. Otherwise, when it crosses n, then embedded unit will terminate and process unsuccessfully, where this variable will not be changed. So let us try to now predict the reliability of this communication module. So we had the first phase was involved with battery net creation. So this is the battery net of this of that algorithm that we have discussed, and let us understand this battery net model. So this place PSRDY is known as where this place represents that embedded unit is ready to send the packet, and with this variable semaphore variable is equal to 0. So if token exists in this place, it means it is ready to send the packet. My system is ready. And but to send the packet, definitely it has to get the request from the display unit. So it has to receive the demand which will be coming from display unit. So this PDSR is representing that embedded unit gets the request from display unit, and then it is going to this transition TS0, which basically represents that embedded unit sends the packet with sequence number 0, and it reset the retry count k is equal to 1 by firing this transition. Then definitely after sending, it has to wait for the acknowledgement, so which is represented by PSW0, and then here it is the data packet has been sent. PS0 as it represents that data packet of sequence number has been sent, and now from the communication it is going to the embedded unit, and this TCOM1, it should represent that display unit sends the acknowledgement to the embedded unit with sequence number 0, and it was waiting for the acknowledgement. So definitely when it so it will be here, the acknowledgement is received PR1R, and it was waiting, so both the tokens can be pulled out, and again it will be ready to send the next packet. Now one interesting fact, okay, before that there's a failure state also. Suppose after n number of trials it is not able to send, an acknowledgement timer has timed out, which is represented by PT0 and 0. then the process of data send is terminated and it will represent like the data sent was unsuccessful. And as I said, after sending one packet, if you see like in this figure, left half is the mirror image of the right half. The reason is we have taken the two embedded unit for redundancy purpose to improve the reliability, so that if one embedded unit fails, the other embedded unit can take up. So the next time we can send from this and then again from this. So it also includes the online testability feature. And now the second activity in this phase is we have to assign the model parameter, and as we are dealing with the safety critical systems which are generally real time in nature, so we can associate the delay uh, in these transitions, and the delay, this is the delay that we have associated. Now this, how much delay has to be put is a very critical decision, and that has to be taken by experts elicitation approach, or the similar kind of projects experiences, design specifications, the operational profile. So these are the subject. This quantitative derivation is from the qualitative data. So this is a very critical, and the entire thing will definitely depend on these data. Now if you can run, there are several tools which can run the PatriNet model, and we have used a tool TimeNet which can run this model, and it can give the throughput of each of the transition. Throughput is nothing but it is in transition rate. It means number of transitions per unit time of that particular transition. And then we can now next one we can create the reachability graph that we have already seen how we can create. So we have to just specify the markings, and marking it was nothing, it is the initial state which is represented by the distribution of the tokens. So if you see in this, this is the initial state, and the mark, and the only this PS star dy and PDSR contains tokens, and this transition is fireable because of it meets the fireability criteria, and after firing, one token will be deposited here and one will be here. So in this way we can in the earlier state these are the tokens, and then it has been deposited here. So this is, in this way we can create we can generate all the markings, and the markings can be tangible in nature or vanishable in nature. If I have associated some delay, it is tangible in nature, otherwise it is vanishable in nature. And then this is the reachability graph which we have shown in the pictorial format, and this can equivalently be transformed into Markov chain. So one these are the markings which are representing the states. So these are the states, and the noticeable fact in this marking is that can be seen is M3 and M8 was the unsuccessful state, because here the packet has not been reached. Next then we can create the generator matrix that we have already seen, the transition rate matrix, in which we can put we can mention all the state in row and column, and we can see like from this figure, from M0 there is a transition to M1. From M1 there are the two transitions, one to M4 and one to M2. So here from M0 there is transition to M1. From M1 there is transition to M2 and M4. But as we have seen this equation, that sum of all the transitions from one state to another is always be 0. So accordingly we'll have to adjust the diagonal elements that we have already seen the equation. So accordingly, we have adjusted the diagonal elements, and we can put these values from here, from this table. And just for the mapping purpose, we have put it like lambda1, lambda2, lambda3, like this. So we can calculate the transition rate matrix, and then we can find out a transition probability matrix, which is by the simple formula. If suppose I want to find out the probability of my transition probability from state I to J, it can be written as transition rate from state I to J, and we have to normalize this transition. So by to normalize, we have to sum up all the transitions. So, but if I is equal to 0, it is 0. So accordingly, we can create the transition probability matrix. So this is the transition probability matrix. Now we have to use the two important equations that we have already seen. Let me go back to that particular slide. The two important equation was this. One is the sum of the total probability is equal to 1, and second one is this. So this is means all as m0 plus up to m9 is equal to 1, and this we are using like this. Yes. So this is equal to the same states and to the transition probability. Now we can solve these two equations to find out the transition, the state probability, and so these are the state probabilities from M0 to M8, and we have seen in this formula this M3 and M8 are the unsuccessful states. So what we can do, we can add M3, the value of M3 and M8, and we can subtract it minus by 1. So this will give the reliability of the overall communication module, which is 0.99603, which is subsequently very good. So that's all I wanted to conclude. So here we can see like how we can demonstrate or how we can quantify the reliability of the overall system. And if your system is large, probably we can segregate into various components, and then we can solve the reliability.
Yeah, thank you, sir. Thank you very much. And I am a PhD scholar, Kaivalya
Okay,
Prasad Panda, in the Department of Electrical Engineering, NIT Meghalaya. So
okay,
Professor Panda is in a meeting now. I think by 1:45 or 2 o'clock meeting will be over.
okay.
So we'll conclude here the sessions, and I request all the participants to ask if you have any question regarding the reliability study. Sir, I have one question actually.
Yeah, please tell me.
This reliability study, one of our scholar, PhD scholar, she was also working in the photovoltaic system,
Mm-hmm.
in this grid microgrid systems, reliability
Mm-hmm.
study of the microgrid systems, and she was also doing this Markov chain analysis and all. So, in terms of this PV system or smart grid applications, if you can tell which method or best suitable for reliability analysis any recent you can suggest?
See, the first of all, there are the two things. One is the reliability prediction, and one is the reliability estimation. Now, if you talk about the reliability prediction, as I have discussed, the PatriNet model is a very good model because it is able to capture all the dynamics of the system, and it is able to model any kind of systems also. So definitely it can be used for this purpose to predict the reliability. Only the thing is, if you remember the one slide where we had to input the important parameters.
Yes, sir.
So giving those parameters is very critical because your reliability will the as accuracy of the reliability estimate will definitely depend on those parameters. So the expert elicitation approach is very much important. And second one, when I was talking about the reliability estimation, where we can use the fault trees. If we will be coming, we will be able to know the reliability of the basic components by applying AND or or gate logic. So if you see the various military standards and nuclear energy systems, these are using even in the electronics when we are using the embedded systems. So these are the methods which can use where we are not having any kind of experience on the similar kind of application, and having very less knowledge. So these kind of estimation techniques can be used in that purpose, for which the reliability of the basic components can be collected from the generic database. There is a huge database available. Even if you are talking about the component reliability or mechanical system reliability, huge database sources are available. We can use that data, and we can derive the probability distribution of that data, and we can see from your observation day of your particular system. We can also refine that data using Bayesian techniques or feedback mechanism. And ultimately, reliability is all the game of the data. If you do have the accuracy of the data, your estimation will be accurate.
Okay. Thank you, sir.
Thank you.
So we have another question from one of the participant.
Hmm.
I think he left just now.
Yeah.
He was asking about any stochastic methods.
And
Is there any stochastic methods?
stochastic methods, as I said, stochastic process. He is written any example of stochastic process. So
Yes, 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 correct.
stochastic process are those processes which contain some randomness. Okay, and
Okay.
I have already uh, very clearly specified whatever the system which has been created by the human are stochastic in nature only, because it contains some randomness, it contains some kind of uncertainty, and that is why we have to talk a lot of about uncertainty analysis. What are the randomness of that system? So every man-made processes are the stochastic processes in only, while the processes which are governed by the law of nature, those are the deterministic processes basically.
Okay.
Okay.
So I hope the participant got the answer. Sir, we'll conclude here. And
Okay. Okay.
I
Thank you.
thank on behalf of Professor Panda and NIT Meghalaya
Yeah.
for delivering a nice lecture on reliability analysis. Definitely, I think in future the participants will be able to apply this reliability analysis in the photovoltaic systems, because nowadays it is in a very emerging field of research, and in the smart grid application also it can be applied. So